Hello and welcome. Today we're going to look at electromagnetic induction. First thing that we'll discuss is the induced EMF in a wire. So as we've discussed in the previous section, that when we have a current in a wire and they are moving, a moving current produces a magnetic field. Okay, so as this current is moving, we've used the right-hand rule. Let's say it's moving that way. We use the right-hand rule and we show that the current's moving that way, creating a circular magnetic field around it. What if I now, it's a moving current, magnetic field, so there are three components. We have force, because the current is forced to move. We've got current and we've got our magnetic field, so FBI is all there. So if I rearrange the scenario and I have my electrons inside a wire and I put it inside a magnetic field and I literally move my wire up and down, so there's movement, there is a magnetic field, and there is the electrons. Now the same principle is going to apply. So since current moving creates an electric field, if we move inside an electric field, a wire, that will produce a potential difference. So the electrons will start flowing. If it's just a simple wire, we'd find all the electrons flowing to the one side, causing a positive and a negative side. If we connect that wire to a circuit, say there, and we move it up and down, our lamp will start shining and we will create a flow of current. Also remember, current and EMF, voltage is friends. So whenever we're inducing a current, we can put an ammeter here, or we can even put a voltmeter here, because the voltmeter will measure the difference in that. Okay, so moving current creates a magnetic field. How do we increase this moving a wire in a magnetic field creates a current? How do we increase the size of this current? Either by making the magnet stronger, or moving it faster, or by adding more loops, and then we make a coil inside. So we'll look at that just now. So what does an induced EMF in a coil look like? So here we can see a coil. We've got a magnet, okay, and either the magnet must move through the wire or the wire must move through the magnet. So in this case we've got a moving magnet, and as the magnet moves it causes the electrons to move. Okay, and we'll see that the direction of the motion, we'll discuss that later. So I can either move the magnet or I can move the wire. Okay, so by adding more loops, okay, we can increase the amount of electricity produced, the amount of current. Okay, if we have a big area, okay, that also increases the amount of electricity that can be produced. So the question is, why does this happen? It has to do with the magnetic field lines cutting through the wire. Okay, and here we can see the magnetic field lines and how quickly they cut. Okay, so obviously the more loops there are, the more wires there is to cut, or wires that the magnetic field can cut through. So the EMF induced and the current induced is directly proportional to the rate, how quickly, or the time it takes for the magnetic field lines to cut through the coil or the wire. So if we do it quickly, we'll have a big current, and if we do it slowly, we'd hardly have anything. Okay, because it's got to do with the rate at which it moves through. So if we continue to look here, we've got our north and south, we've got our coil here, And what we can do is we can start rotating this coil. If we want to make a current, we now physically rotate it, okay, through our magnetic field. So we cause a force to rotate my coil. That can be wind pulling it or something like that. Even an electric motor, we call that a electric generator, which you use diesel. So you make this coil move in some or other way, either with wind or with boiling water in power stations, or an electric generator, which makes this coil move. And the moment the coil starts moving, we generate a current inside that coil, and that's how we generate electricity. Now, once again, this depends on the strength of the magnetic field, how quickly this coil rotates inside. So we make it rotate, and then we also the number of loops and the area of the loops. So there's a few things that we want to observe here. If we take the north towards it, it deflects to the negative side. Okay? If we swap our magnet around and we take the south towards it, deflects to the positive side. So north and south gives us opposite deflections. Okay, so north coming towards negative, and if we've got a south, south coming towards gives us a positive. But if I take my north away, north going in negative, north going out positive, and south going in positive, south going out negative. Okay, so these are some of the observations that we can make by looking at this experiment. Also, what we can see is the moment the magnet stands still, far or close, when there's no motion, there's no current. Okay, I want you to continue reading through the current unit and making sure that you've got all the other info. So just read through the chapter that we're busy with, and then make notes if you've got any questions. Thanks.